All right, so today in Algebra 2, we're going to look at the first section of 2.7, linear quadratic systems. Okay. We're going to look at how can you solve a system of two equations or inequalities in which one is linear and one is quadratic. Remember that linear means a line and quadratic is a parabola. So first thing we're going to do, number one, I want you to draw a parabola and a line on the coordinate plane. So anywhere. So let's say I just draw my basic parabola. The y equals x squared. So there's my parabola. And then draw a line. Anywhere, draw a line. Okay, I can draw a line right there. Okay. What do I notice? I notice that the line touches the parabola twice. Okay, so on this one that I drew, I have two intersections. So I want to see, is that always the case? So over here on this other one, we're going to sketch another parabola on the coordinate plane and use a straight edge or just a ruler or just draw a line to investigate the different ways a line and a parabola may intersect. So again, I'm just going to draw my basic y equals x squared parabola. So first off, what if I drew a line down here? Okay. If I draw the line down here, I'm going to label this line number 1. But if I drew a line like this, I'm going to draw that, label that line number 2. And then I'll draw this line right here and label that line number 3. And so then question 3 wants to know how many different numbers of intersection points are possible between a quadratic function and a linear function. So if I look at line number 1, so line number 1 that I drew, I can see that this line down here is never going to intersect that parabola. So I can have where they never intersect. This would be 0 intersection points. If I look at line number 2 that I drew, I see it's only going to touch my parabola once. So I may have where it may intersect once. And where it actually intersects, this is called the tangent line. Okay, so it's called a tangent line. If your line only touches your parabola one time, that's called the tangent line. And then I'm going to look at graph number 3, line number 3 that I drew. That one intersects twice. So I may have 2 intersections. So may intersect twice. So our possible intersection points between a quadratic function and the linear function are 0, 1, and 2. So next okay, so now that we know our possible answers are 0 intersection, 1 intersection, or 2 intersections, we're going to determine the number of solutions for a linear quadratic system. So number 1, how many real solutions does the system have? And again, real solutions, so we're looking for actual intersection points. Okay, so if I want to graph these, okay, so if I graph y equals x squared, remember that is just my parent function. I pick -2, -1, 0, 1, and 2. 0, 1, 4, 1, and 4. So that's the parabola that we had been drawing up above. So I'm going to draw that parabola. Remember, it's a U shape. Now I want to graph y equals 2x. This is my line. Remember, our lines look like y equals mx plus b. So identify my slope is 2. My y-intercept is 0. So that means if I start at 0, I go up 2 over 1. Up 2 over 1. Up 2 over 1. Or I could have gone down 2 over 1. So I'm going to draw that line. How many real solutions do I have? So it intersects once and twice. So I have 2 real solutions because the line intersected the parabola twice. Okay. Let's do some more of those. So on the back, number 2, how does modifying the linear function in the system affect the number of solutions? So let's look at, again, y equals x squared. We know we're going to be 0, 0, 1, 1, 2, 4, and then negative 1, 1, negative 2, 4. So the same parabola that we're going to draw. So this time, y equals 2x plus b. We want to know, what does modifying that b do? Okay, so let's try a b of negative 1. So then my slope is 2. So I would come down here to negative 1, up 2 over 1, up 2 over 1, 2 over 1. I could go down 2 over 1. So my line right there so I have one intersection point, and that's at the tangent. What if I tried a b of, let's say, negative 5, and my slope is still 2? So this time if I come down to negative 5, up 2 over 1, up 2 over 1, up 2 over 1. This is my line. I see that that line is never going to intersect my parabola. So here I have no intersections. So you can see how changing the b value will change how many solutions we have. Okay, so this one would have no solution. If b was negative 5, if b was negative 1, I had one real solution. On number 1 on the previous page, when b was 0, we had 2 real solutions. So number 3, let's determine the number of real solutions to this system. So we're going to graph 3x squared this time, make our xy table. Again, we're going to pick negative 2, negative 1, 0, 1, and 2. 0 is still 0. If I plug in 1 squared is 1, 1 times 3 is 3. 2 squared is 4, 4 times 3 is 12. And I know it's symmetric, so I know I'm going to get 3 and 12 up there as well. So let's plot these points. Over 1 up 3, 2, 12. Off my graph. So we're up here, so this parabola, something like that. Now the graph y equals 3x minus 2, my slope is 3, my y-intercept is negative 2. So negative 2 is where I start, up 3 over 1. So I see that I'm touching my parabola right there one time, up 3 over 1, up 3 over 1, and I can see that it's never going to touch the parabola again going out this way. So I have no real solutions because my graphs never intersect. So now we want to solve a linear quadratic system using substitution. Remember substitution and elimination from our previous chapter. So I have the system y equals 3x squared plus 3x minus 5 and 2x minus y equals 3. I already have this one solved for y, so I'm going to take this entire thing and plug into that equation for y. So I'm going to rewrite the bottom equation, 2x minus, I'm going to put parentheses. In place of y, I'm going to plug in 3x squared plus 3x minus 5, and then continue writing this equation equals 3. I'm going to distribute my negative, so I get 2x minus 3x squared minus 3x plus 5 equals 3. I need to get everything on the same side. So I have negative 3x squared minus x, and then when I subtract 3 over, I get plus 2 equals 0. I need to go ahead and take that negative 1 out, because if I'm going to factor, I can't factor with the negative in front, so this is going to be 3x squared plus x minus 2 equals 0. I want to try to factor that. Okay. So multiply 3x squared and negative 2. So I'm looking for a negative 6x squared that adds together to get a plus x. So what can I multiply together to get negative 6x squared but add to get a positive 1x? That would be a 3x and a negative 2x. So out here, that negative 1. So when I factor this, I'm going to rewrite this 3x squared. I'm going to rewrite the plus x as minus 2x, excuse me, plus 3x minus 2. All of that equals 0. So I'm going to factor by grouping. So 3x squared minus 2x, the only thing they have in common I can take out is an x. So then I get 3x minus 2. 3x minus 2, the only thing I can take out is a positive 1, and I get 3x minus 2. I got the same thing in parentheses, so I know that I factored it correctly. So I have one factor, 3x minus 2. My other factor is the x plus 1. This negative 1 that I pulled out has no bearing in this right now. So all of that is equal to 0. So I need to solve both of these. So this one, when I solve this, I get x equals 2/3. Here I get x equals negative 1. It asked me to solve the system, so I need x and y. Right? So I can plug this x into either of these equations to solve for y. If I take 2x minus y equals 3, and I get the y by itself, I would end up with y equals 2x minus 3. So I'm going to use this equation because I think that would be easier than having to deal with the x squareds. So if I plug in x equals negative 1, this is going to be the easier one. So I get y equals 2 times negative 1 minus 3. So negative 2 minus 3, I get y equals negative 5. So now I'm going to plug in x equals 2/3. So y equals 2 times 2/3 minus 3. So here I have y equals 4/3 minus 3. I can get a common denominator. So this is really 4/3 minus 9/3. So here I get y equals negative 5/3. So my two answers, I have two real solutions. One of them, when x was 2/3, y was negative 5/3. The other one, when x was negative 1, y was negative 5. Those are my two solutions. Okay. We're going to do another one of those. So again, solve using substitution. Again, I notice that the first one is already solved for y. So I'm going to take that whole thing and plug into the second equation where I see the y. So this whole thing in here. So I have 2x minus, in parentheses, 2x squared minus 6x minus 8. All of that equals 16. Again, I'm going to distribute my negative. So I get 2x minus 2x squared plus 6x plus 8 equals 1. Get everything on the same side and set equal to 0, combine like terms. So I get negative 2x squared plus 8x plus 7. This was equal to 16, not 1. So that's going to change that answer right there. Sorry about that, guys. So let's see, 8 minus 16, that becomes minus 8 equals 0. So I have negative 2x squared plus 8x minus 8 equals 0. I can pull a negative 2 out of everything, and I get x squared minus 4x plus 4 equals 0. Notice now x squared minus 4x plus 4, I recognize that as a perfect square trinomial, so that's going to factor one set of parentheses quantity squared, x minus 2. When I'm solving this, remember this -2 doesn't have any bearing on it, so I take x minus 2 equals 0, I get x equals 2. So I'm going to have one answer here. Again, I'm going to take the second equation, 2x minus y equals 16, get the y by itself, so I end up with y equals 2x minus 16. I'm going to plug x equals 2 in there, so y equals 2 times 2 minus 16. So 4 minus 16, y equals -12. So my one solution here is 2 comma -12. Let's do another one of those, solve using substitution. So again, take the bottom equation, 4x minus, in place of y, put everything from the top, -3x squared, plus x plus 4, all of that equals 2. Distribute my negative, so I get 4x plus 3x squared, minus x minus 4 equals 2. Put everything on the same side of the equation and combine like terms, so I end up with 3x squared plus 3x minus 6 equals 0. I need to factor that. I notice I can take a 3 out of everything, and then I'm left with x squared plus x minus 2 equals 0. I want to factor this, so 2 sets of parentheses. What can I multiply together to get -2, but add to get a +1? That's going to be a +2 and a -1. Setting both of these equal to 0, here I get x equals -2 and x equals +1. So I'm going to have two solutions. Again, I'm going to take my second equation, 4x minus y equals 2. I'm going to get the y by itself, and I end up with y equals 4x minus 2. If I plug in x equals -2, y equals 4 times -2 minus 2, so we get -8 minus 2, y equals -10. Now I'm going to plug in x equals 1, so y equals 4 times 1 minus 2, so I get 4 minus 2, y equals 2. So my two answers, -2 comma -10, and 1 comma 2. Those are my two answers. So now let's look at applying a linear quadratic system. So it's a word problem, of course. If we're applying, we're looking at word problems. Alex kicks a ball up a hill for his dog Isabella to chase. The hill is modeled by a line through the origin. The path of the ball is modeled by the quadratic function shown. How far does the ball travel horizontally? How far must Isabella run up the hill to catch the ball? Okay. So I see that this line right here, I want to know how far we're going to have to go up that hill. Okay. She's going to have to run up the hill to catch the ball. I start at 0. Right? I'm looking for basically this distance right here, from here to here. Okay? Remember from our Algebra 1 and even our geometry days, I can make a right triangle, right, in this picture and solve for the third side of my right triangle, the hypotenuse. This side I see, okay, what is my x? They tell me, and then what is my y? So I need to solve the two equations that they give to me, -0.5x squared plus 6x and y equals 0.5x. Okay? So I'm going to set those two equal to each other because that's where they are intersecting. So -0.5x squared plus 6x. When does that equal 0.5x? When do they intersect? When they equal each other. Get everything on the same side, so I get -0.5x squared. So 6x minus a half x gets me plus 5.5x is equal to 0. I notice that I can take out a -0.5 out of everything. So if I pull out a -0.5, I'm left with x squared minus. So 5.5 divided by -0.5 leaves me with 11x equals 0. Pull an x out. I should have put that out up there, so then I get x minus 11. So when I solve each of these, this one gets me x equals 0. This one gets me x equals 11. When x is equal to 0, y is equal to 0. Right, that's this point right here. I need to know what is my y when x is 11. So I want to come over here and plug that in. So plug in. I can pick either equation to plug that into. I think the y equals 0.5x would be the easiest to plug it into. So y equals 0.5x when x is 11. So y equals 0.5 times 11. Y is 5.5. So I know that this, my x was 11, this is 11. My y, this distance was 5.5. So now I can use that to find, I'm going to call that c. We're using the Pythagorean theorem. So remember, Pythagorean theorem says 11 squared plus 5.5 squared equals my c squared. 11 squared is 121. 5.5 squared is 30.25 equals c squared. Add these two together and I get 151.25 equals c squared. Take the square root of both sides. I don't have to take positive and negative here because I know I'm looking for a distance, and so I know I cannot have a negative distance, so I'm only interested in the positive. So we're going to say approximately, so the square root of 151.25 is approximately 12.3. So she has to run approximately 12.3 feet uphill. All right. For today, let's look at one more application problem. So this one says revenue for the high school band concert is given by the function y equals negative 30x squared plus 250x, where x is the ticket price in dollars. The cost of the concert is given by the function y equals 490 minus 30x. At what ticket price will the band make enough revenue to cover the cost? So when will these two graphs intersect is what we're looking for. So set them equal to each other. Negative 30x squared plus 250x. When will that equal 490 minus 30x? Again, I want to get everything on the same side. I want my 30x squared to be positive, so I'm going to move it to the other side. So when I do that, I get 30x squared. Negative 250x minus the 30x we already had over there gets us negative 280x plus 490 equals 0. This is what we want to factor. Let's make our lives much easier and pull out a GCF. So 30, 280, and 490. The biggest thing they all have in common is a 10. So if I pull a 10 out, then I'm left with 3x squared minus 28x plus 49 equals 0. So this is what we want to factor. So multiply 3x squared times 49, and I get 147x squared. And I'm trying to add to get a negative 28x. So what can I multiply together to get 147x squared, but add to get negative 28x? That's going to be a negative 7x and a negative 21x. So I'm going to rewrite this equation. 10, 3x squared minus 7x minus 21x plus 49 equals 0. I'm going to factor by grouping. Again, I know that when I solve, this 10 out here is not going to have any bearing on anything. So 3x squared minus 7x, I can pull an x out of those and get 3x minus 7. Negative 21x plus 49, I can pull a negative 7 out, and I'm left with 3x minus 7. I got the same thing in parentheses, so I know I factored it correctly. So I have a 3x minus 7 and an x minus 7. Solve both of these, and so I get x equals 7/3 and x equals 7. These are my two answers because it says at what ticket price, x is my ticket price, so I don't have to plug anything back in to find my y. I just need to know 7/3. What is that as a decimal, because I'm talking about dollars. So if we do 7 divided by 3, we get x equals 2.30. So between $2.30 and $7 is when they will make a profit. All right, that's going to do it for day 1 of section 2.7, kind of a long day. Tomorrow we will look at graphing the systems and solving systems of linear inequalities.